Hello student friend, welcome for today's lecture on topic powder metallurgy. Today we are going to discuss a topic of powder metallurgy under the subject material science and metallurgy. Now this word powder is uh, we have to think on this word, and whenever the material we are using in its powder form to make a product or to make a useful goods, so that processing of that powder involves the topic title as a powder metallurgy. So, what exactly there in powder metallurgy topic, that we'll see in detail. So, today we'll discuss on characterization of engineering powders, production of metallic powders, then conventional processing, pressing and sintering, then alternative pressing and sintering technique, materials and products from powder metallurgy technique, then design considerations of powder metallurgy. So, let us have what exactly powder metallurgy means. Metal processing technology in which parts are processed from metallic powders. So, here we are first making powder of metals, and from that powder we are manufacturing the products. So, in the usual powder metallurgy production sequence, powders are compressed or pressed into the desired shape and then heated. This heating process we call it as a sintering process or sinter, to bond the particles into hard and rigid mass of required size and shape. So, pressing is accomplished by press type machine using punch and die tooling designed specifically for the parts to be manufactured, and sintering is performed at a temperature below the melting temperature of that metal. So, here this part is important while processing the metal powders. Then why powder metallurgy is important for any engineer? So, powder metallurgy part can be mass produced to near net shape or net shape. It will eliminate or reduce the need for subsequent machining operations. Then powder metallurgy process wastes very little material. About 97% of material is converted into useful product. Then powder metallurgy part can be made with specified level of porosity to produce porous metal parts. So, normally by any other manufacturing process we cannot produce the porous metal part, but this is the technique by which you can produce the porous metal parts. Examples are the filters, oil impregnated bearings and gears. So, where we require the lubrication, and that lubrication is achieved by this porosity technique or porosity in the product. Then more reasons why powder metallurgy is important. Certain metals that are difficult to fabricate by any other method, that can be shaped by powder metallurgy technique. So, manufacturing when becomes difficult, then powder metallurgy is the alternative. For example, tungsten filament for bulb lamp is made by powder metallurgy technique. So, certain alloys, combinations and ceramides are made by powder metallurgy technique. Any other process by that process, it is not possible. So, powder metallurgy compares favorably with most casting processes in the dimensional control, but powder metallurgy methods can be automated for economical production. So, these are the powder metallurgy reasons why powder metallurgy is highly appreciated by any engineer. Then, but there are some limitations as well as disadvantages with this powder metallurgy technique. So, these limitations includes high tooling and equipment cost. So, when we prefer this powder metallurgy technique, then the tooling cost as well as the equipment cost is very high. Then metallic powders are expensive. So when we form a powder of any metal, so that process takes a heavy expenses. Then problem in storing and handling the metal powder. So when any metal is in the powder form, it is hazardous and degrade over a time. So there is a risk of storing the powders. So limitations of on part geometry, because metal powders do not readily flow literally in the die during the pressing. So if the shape of the die is complex shape, then it is very difficult to occupy the entire metal powder into that die cavity. Then variation in density throughout the part may be a problem, especially in complex geometry. So variation in density may occur during the manufacturing of parts by powder metallurgy technique. Then next issue, powder metallurgy work materials. Largest tonnage of metals are alloys of iron, steel and aluminum. They are consumed in powder metallurgy for manufacturing variety of parts. Other powder metals includes copper, nickel, refractory metals such as molybdenum and tungsten. Metallic carbides such as tungsten carbide are often included within the scope of powder metallurgy. So it is quite oftenly processed by powder metallurgy technique. So this is the photograph of different powder metallurgy parts that are manufactured. Say some gears are there, liners are there, bushings are there, some shafts are there, some pinions are there. So are the combined parts which we cannot manufacture by any other technique, which are easily manufactured by powder metallurgy technique. Then engineered powders, engineering powders. Say a powder can be defined as a finely divided particulates of solid. Engineering powders includes metals and ceramic powders. Then geometric features of engineering powders are particle size and distribution, particle shape and internal structure, and the surface area of powder. So surface geometry. So these are the important parameters of any powder. Then how the measuring particle size of powder? Most common method uses screening of different mesh size. So this powder manufactured is screened by different sieves or meshes, and mesh count refers to a number of openings per linear inch of the screen. So how many openings are there in that area? So that number of opening indicates the number of the size of that. Mesh count of 200 means there are 200 openings per linear inch. Since the mesh is square, the count is same in the both direction, and the total number of openings per square inch is 200 raised to 2, that is 40,000. Higher the mesh count means smaller the particle size. So this is the fundamental thumb rule of any powder particle size. Now here this figure indicates the mesh size and the mesh opening for sorting the powder particles. So here what we are observing, so square mesh is there and some particles are passing through that square mesh, whereas some are not passing through the mesh. So the particle which passes through that mesh or through the opening, that particle are assigned to the mesh number of this size. Then several of the possible ideal particle shapes are possible in the powder metallurgy. So these shapes are round shape, then spherical shapes, then cylindrical shapes, spongy shapes, acicular shapes, flaky shapes, cubic shapes, or aggregated shapes. So some shapes are smaller in size, but they form aggregates. Aggregates means they come in contact with each other. So these are the several possible powder shapes. Then interparticle friction and flow characteristics of powder metallurgy. Friction between particles affect ability of powder to flow. So whenever there is a friction between the particles of the powders, they will affect the flow ability of powder and get spackly tight. Then a common test of interparticle friction is angle of response, which is the angle formed by piles of powders as they are poured from a narrow funnel. So when you pour a particle or the powder through a narrow funnel, how that particles get stacked below that funnel, so that decides the angle formed by the piles. So then this is the indication of that angle formed below the funnel. So interparticle friction as indicated by the angle of response of the pile of the powder poured from the narrow funnel. So larger the angle indicate greater the interparticle friction. Then what is the observation? Small particle size generally show greater friction and steeper angle. So when the particle size is very small, they show the greater friction and the steeper angle. Whereas spherical shape have lowest interpartial friction. So whenever the shape is a spherical shape, the interpartial friction is the lowest value. As the shape deviates from the spherical to spherical, friction between the particles tends to increase. So when the shape changes from spherical to any other shape, the friction between the particles tends to increase, and it is obvious. Okay. Then particle density measure. So how to measure the particle density in an volume? So true density, density of true volume of the material. Then the density of the material if powders were melted into a solid mass. So how much melt we'll get from a solid mass, that is the density. And the bulk density of powder in the loose state after pouring. So when you get a loose state after pouring, that is the density of powder. Because of the pores between the particles, bulk density is less than the true density. So we know that bulk density is lesser than the true density. In true density, we consider it as a homogeneous or the entire integrated solid. So packing factor or the equal to bulk density divided by true density. So we are applying the pressure and the temperature to get the packing of powders. So that packing factor is the ratio of bulk density divided by the true density. So typical value of loose powder ranges from 0.5 to 0.7 as a packing factor. If powder of various size are present, smaller the powder will fit into interstices of larger one that would be otherwise taken up by air or thus lighter, thus higher packing factor. So packing can be increased by vibration given to the powder, causing them to settle more tightly, and pressure applied during the compaction greatly increases the packing of powder through rearranging and deformation of particles. So this is important, how to enhance the packing factor of any powder and reduce the of course the packing factor and porosity. One more term is the porosity, the ratio of volume of pores, that means empty spaces in the powder to the bulk volume. So this ratio will reduce when you apply more packing. So principally porosity plus packing factor should be equal to 1. This is the formula, and the issue is complicated.